Okay, so here in Unit 8, we're going to look at thermal energy and laws of thermodynamics. So the first topic, so a lot of this may just sound like a review of chemistry because a lot of this was covered in parts of chemistry. We're going to look at calorimetry, we're going to look at heat transfer, we're going to look at temperatures, and so we will do some ideal gas law. We'll also talk about PV equals nRT, right? That ideal gas law. We'll also talk about just the different things associated with heat. So there's a whole section in physics centered around heat and the transfer of heat and thermodynamics. So let's start off very simple. Like this should be just a real quick review of a topic you've been talking about ever since like elementary school. So the first thing we talk about is we're going to focus on temperature. So the first thing is temperature, right, is proportional to the average kinetic energy of particles in a substance. When the material is considered to be hot, the particles are moving faster and thus having a greater temperature. Right? We're no longer really going to distinguish between hot and cold, right? That's going to tell us how the particles are. So this is going to be high temp, right, which means fast particles. Cold is going to be low temperature, right, and it's going to be slower particles, okay? And so that's what we're going to focus on, right? Really hot and cold is our senses of our feelings for like the heat transfer, okay? So we're going to go away from hot and cold, and we're going to talk about high temperature, low temperature, fast moving particles, slow moving particles. So the total amount of energy in a substance, is the sum of all its kinetic energy, is what we refer to as internal energy or thermal energy. Now, when we were talking about energy before, this is one of the ones that we kind of disregarded because there was no friction. So adding thermal energy to a system is known as heating, and removing it is known as cooling, right? And so when I add energy in, I'm increasing, right? I'm making the particles travel faster, heating the substance, which means I'm raising the temperature. And if I'm removing, right, I'm going to slow those particles down to lower their temperature, right? And that's what we call cooling. So when two objects are in thermal contact with each other, there's an exchange of heat, okay, or thermal energy. So if I have hot and cold, right, there's going to be an exchange, right, of thermal energy, and it's going to flow from hot to cold. Okay, that's how all heat flows, okay, or all thermal energy flows. So it's the hot particles trying to transfer the energy to the cold particles. Now, the reason why this happens is because there's a difference in temperature, right? And so the exchange of energy stops, right, when the temperatures are equal, right? And we call this thermal equilibrium. Right? Again, that word equilibrium means balance. So what this is saying is that our temperatures are balanced. Now, thermal equilibrium is the basis of what we call the zeroth law of thermodynamics. And so you can see part of this unit is going to focus on laws of thermodynamics. So what happens is that objects in contact with one another are in thermal equilibrium if they have the same temperature. Right? This is the basis of thermometers. So once you take your temperature, you're trying to determine the equilibrium point between the thermometer and yourself. Okay. Now, in general, heat is the energy that is transferred between the objects because of the temperature difference. Right? So we talked about how the total energy was thermal energy, but what we're doing is we're transferring the heat. Now, because heat is essentially energy, right? We're going to measure that in joules. Last year in chemistry, you used calories, and we're going to talk about that here in a second as well. All right. Now, what happened was they originally thought there was a substance called caloric, that was exchanged, hence the unit calories, right, in chemistry. So they actually felt that there was a substance, right, not just energy that was transferred, but they thought there was a substance that was the one that was causing this transfer, this difference in temperature. Okay, so if there is a transfer of thermal energy or a flow of thermal energy from hot to cold, it simply means that the total energy of the hot object decreases, and the total energy of the cold, I put brick because where I got this was talking about a hot and a cold brick, the cold object will increase, right, or increases. So if I go back to that picture, so the particles here, right, are transferring energy to the cold particles to get these to move around more, right, increasing the temperature or the thermal energy here and decreasing it at TH, but TE, right, so we're increasing the thermal energy there, but we're decreasing it on the hot side, right, until we get to a point when they're in equilibrium, right, when they reach that same temperature. Now, how do we measure this, right? And so we'll talk about a variety of temperature scales, right? And we use them for everyday situations and in physics. Now, the most common temperature scale used in the world is Celsius, right? You see it as degrees C, and the boiling point of water, right? Because that's how we really focus on these scales. So the boiling point of water in Celsius is 100 degrees Celsius, and the freezing point is 0 degrees Celsius. I do want to point out that the melting and freezing point are the same point, and the boiling point and condensation point are the same point, right? So for water in Celsius, it's 100 degrees, not for melting. Oh, should have picked the eraser. There's the eraser. So the melting point is 0 degrees Celsius. The boiling point or condensing point is 100 degrees Celsius. Okay. Now, in the United States, of course, we've got to be just a little bit different. We use what is called the Fahrenheit scale. And yes, they're actually named after people, right? I believe they were both German, or at least that Central European, Germany, Austria, somewhere in there. Okay, so the boiling point in this scale is 212 degrees Fahrenheit, and the freezing point or the melting point is 32 degrees, right? So if I go back here, so in Fahrenheit, the melting freezing point is 32. In Fahrenheit, the boiling or condensing point is 212. So one thing you know, it's not like a one-to-one change. So this is when you have to convert, you get that weird 5/9, 9/5 kind of running around. So if I want to go from the Fahrenheit temperature, right, if I want the Fahrenheit temperature from Celsius, I'm going to do 9/5 the Celsius temperature plus 32. Okay, and if I want to go the other way to get the Celsius temperature, if I do a little algebra, I'm going to get 5/9 times the Fahrenheit temperature minus 32. So just real quick, if you do this for like 0 degrees, right? So 0 degrees Celsius, if I do 5/9, put in the wrong one. All right, so if I do, all right, TF equals 9/5 times 0 plus 32, right? I get 32 degrees Fahrenheit, right? They match up, and let's say I want to do 212, right? So TC equals 5/9 times 212 minus 32, right? And so this becomes 280, okay? And then 5 times 280 over 9 is 100 degrees Celsius, right? And so there's your 212, okay? All right, so now here's just another, so that was converting between the boiling points and all that. Let's look at a different conversion. So on a fine spring day, you notice that the temperature is 68 degrees Fahrenheit. What is the corresponding temperature on the Celsius scale? And if that temperature on a brisk morning, winter morning, is -2 Celsius, what is the corresponding Fahrenheit temperature? All right, so here we're going to go from, we want the TC, so we want the Celsius temperature, so we're going to do 5/9 times TF minus 32, So I'm going to go TC equals 5/9 times 68 minus 32. So this is going to be 36. I'm doing 5/9 times 36, and that's going to give me a temperature of approximately 20 degrees Celsius. Now, if I want to do the cold winter morning, okay, I'm going to find the Fahrenheit temperature. So I'm going to get 9/5 times the Celsius temperature plus 32. So TF equals 9/5 times -2 plus 32. So it's going to be -18/5 plus 32. So that's roughly 3 point something. So it's going to give me a temperature of 28 degrees Fahrenheit. Okay, so you can see that this is less than 32 degrees Fahrenheit, which is the melting point / freezing point of water. Okay, now here in physics, and this is very important to note, is that we're going to use a completely different scale. Okay, there's a couple other temperature scales that exist, but the one that we're going to focus on is that we're going to look at the lowest possible temperature, and we call this absolute zero. Okay, so absolute zero is the temperature below which it is impossible to cool an object. And so absolute zero has a Celsius temperature of -273.15 degrees Celsius. All right, and so how this came about was Lord Kelvin, right? Notice that when he plotted the temperature, and you stop at the y-axis, you stop at, right, 0 degrees or 32 degrees Fahrenheit. But he says, okay, what happens if I extend this line back? What do I get? So he theorized that there was a 0 degrees, right? There was this floor temperature, okay, which he predicted out to be -273.15 degrees Celsius, okay? And so this, right, this process is, okay, this is what, because I think it was a kinetic energy to temperature or temperature to kinetic energy, right, something along those lines, okay, because there's another equation associated with it here to do some calculations, but he extended it back and got to this -273.15. Now, they named the temperature scale in honor of him, so the Kelvin scale is based on this existence of absolute zero, okay? So what this is saying is that the 0 point of the Kelvin scale, so this absolute zero, is set exactly at absolute zero, meaning this scale has no negative temperatures, right? So Kelvin cannot be, right, less than zero, right? So it can't be negative because there's a floor, right? So if I look at the temperature scales, my floor is 0 degrees Kelvin or -273.15, right? Now the thing to note is there's no ceiling, right? So I can go as high as I want on this temperature, on any of the temperature scales, okay? Right? So there's a floor, but there's no ceiling for temperatures. Okay. Now to convert between Celsius and Kelvin, we're just going to add 273.15 to our Celsius temperature. And so note, when you see T with no subscript, that is Kelvin. So that is our Kelvin scale. Okay, and notice that whenever I wrote Celsius or when I write Fahrenheit, I put C or F. Okay. Now let's look at a conversion. So we're going to start at Fahrenheit, convert to Celsius, and then convert to Kelvin. Okay, so this is very common to kind of take it slow, right? And so part A says, as a cold front moves through your area, the outside temperature drops by 35 degrees Fahrenheit. What is the corresponding temperature change in degrees Celsius and kelvins? So I'm going to do my Celsius conversion first, right? So I'm going to say TC equals 5/9 TF, 5/9 times TF minus 32. Right, so I get 5/9 times 35 minus 32. And so this ends up being 3, so it's 15/9. So 15/9 is 1.7. It's like 1.66, right? So it's 1.7 degrees Celsius, okay? And so now I have my Celsius temperature. Now I'm going to convert to my Kelvin. So I'm going to say temperature in Kelvin is TC plus 273.15. And so all I do is say 1.7 plus 273.15, and I get a Kelvin temperature of 274.85 Kelvin. Okay. When you write the Kelvin, no degree symbol. It's just a capital K. Okay. So what we're going to do in the next video is we're going to look at expansion. So as we change the temperatures, right? How do solids, gases, liquids, how do they react, and so forth.